5 seconds. Okay, let's go ahead and get started. So this is lecture number 2 of the Wireless Communications Lab course. And as promised, I am shifting from PowerPoint to the document camera. My intention is, in addition to making these lectures available through Blackboard and eventually through YouTube, I'm also going to upload a scan of all of my notes as well. And then further, keep in mind that I've created the text essentially from my lecture notes. And so for the most part, everything I'm talking about is going to be also in the book as well. So, you know, if you're the kind of person that gets distracted by taking notes, don't feel like you have to take, you know, notes in detail, since I will give you the slides and everything is in the book anyway. This is probably one of the few lectures that deviates a little bit from the content of the book. So I'm using these nice printed dividers to help me if I want to cut the video later, so I can divide it up into shorter lectures here. So this is lecture 2. Now we're going to start off with the first part of today's lecture, which is the introduction to digital communication. And then with every section topic, so this is essentially we're going to cover 2 sections today. I'm going to also list here learning objective, and so this is what I hope that you are able to accomplish after seeing this part of the lecture. And you know, today's lecture is a lot of high-level overview, so it's not as specific as you will see in future lectures here. But you know, so for this lecture, we're going to talk specifically about digital communication, and then you should be able to essentially explain why digital communication is important and relevant. You know, give some examples of digital communication systems. And then connect that to digital signal processing. So that's it. So now we get started with the main part of the lecture. So introduction here. Let's see. Okay. So I have to maybe calibrate the screen a little here. Looks good. There we go. All right. So introduction to digital communication. Now, I have to confess it's very strange for me to be sitting down and lecturing, but given the height of this table, if I stand up, I'm going to have back problems by the end of the semester, so hope you can bear with me here. And then also I assure you that I don't write any neater on the whiteboard. But apparently we could use the whiteboard as an alternative, and I'm happy to explore that if you all want to do that, because apparently this whiteboard is all digital, and so we could write on it and I could evidently print it out. That would be cool. Okay, so you know, first of all, you know, this part of the lecture is a lot of terminology and a lot of you know, background that if you've taken the digital communication prerequisite, you've already seen before. But if you come from one of the DSP classes, you may not have seen this here. So first, I'm going to talk a little bit about the principles of communication itself. And the other warning I have for you is that I find it very hard to spell and talk at the same time. So, you know, you have to use some interpretation of my creative spelling at times. That is a C right there. So principles of communication here, if you open up kind of like a standard digital communication textbook, information theory book, you'll see that there's 3 pieces in a communication system that are important. First one is the transmitter. And the transmitter is what is generating the information or source. So you see this term used, you know, abstractly, source, especially in information theory. So source is essentially just where the information is coming from. So the transmitter is, getting this information somewhere and is in charge of sending it. The second piece abstraction that is important is the channel. And so the channel transfers a signal from essentially the source or transmitter to the receiver. So you can think about linear systems terminology. We might call the channel a transfer function. So it's essentially our abstraction for what's happening between the transmitter and the receiver. And so through a lot of this course, we're going to spend time on modeling, developing a model for this channel, a mathematical model, and we'll look at different aspects of it. But it'll end up being typically a model that has a linear time invariant component and an additive noise component. So it's going to be a stochastic channel model. So that's the transmitter. That's the channel here. So one thing I want to emphasize here is that the channel, it also includes the propagation medium. So it includes whatever's happening in the environment, as well as what can be happening in the analog circuitry. So the effects of having non-ideal circuit components and are typically also lumped into this whole thing that we call channel. So transmitter, channel, and you can probably guess the third one here, that's receiver. So the receiver processes the received signal, and it's often referred to as the sink of information. So for here, think like kitchen sink. You turn the water on, it runs down the sink here. So the receiver, the information is sinking into the receiver in some sense. So a lot of, and this is a communication system that's essentially like a single user system because there's one source, there's one channel, and there's one receiver. And we'll see somewhat later in the course that real communication systems, there's potentially many sources, many transmitters, many channels, many receivers. But for the most part in this class, we focus on just this single communication system for one transmitter and one receiver. So this is the idea of digital communication. This is the idea of just communication in general here. Now, one thing we also need to specify is what is information? And so information has a very technical definition, and there's a whole set of courses and research built around this called information theory, of all things. And it essentially, for the transmitter sending a message, and for this message to be informative, it should be something that is unknown to the receiver. If the receiver knows that you're going to send the message read, then it's kind of arguable if any information is actually sent. And so in information theory, to define these notions of information as a function of conditional entropy and entropies of the signals. And essentially, there has to be some randomness in the message at the receiver here. And it's like, so the mutual information, roughly speaking, is like the difference in this conditional entropy versus the actual entropy of the message, which is basically just saying that there's something left in the signal, so given at the receiver. So so information is going to be stuff the receiver doesn't know. And why I want to make this long-winded point is that we're also going to be sending signals that the receiver does know, and that's going to form what we call training information or pilots or side information. And communication systems use an incredible amount of known signals as well to facilitate communication. And so we're going to see that in subsequent lectures and say, I can't remember now, probably starting at lecture 12, let's say. So that will be not information. Okay, so let's see. I'm thinking there's no easy way to roll the paper up here, so I'm going to switch out the paper. So these numbers up here on the top are primarily just for me, so when I scan the notes, I put them in the correct order. So now let's spend a little bit of time talking about analog and digital communication. And so this is a well-known topic. Just realizing there's no clock in here, so I have to look at the time here. If I look at my phone for the time, I'll see some interesting message on there, and then I'll be compelled to respond to it. So this is why having a watch is useful. Have you all seen this before? This is called a watch. Before we had smartphones and phones and things, we used this to actually tell what time it was, believe it or not. Yeah, that's good, but then I have to look over here for the clock. So, yeah, for me, I think this is better here. But yeah, that's a clock. Yeah. You can probably make a lot of money selling a clock that looks like a big phone, right? Yeah. And I hope there's no entrepreneurs watching this video, because they're going to get all these ideas from me and then make a lot of money. Yeah, man. Okay, so analog versus digital here. These are the two common types of communication. And until about 5 years ago at UT, we had classes that covered both of these topics separately. And since we have eliminated the topic on analog communication. So first, let me just define a little bit what these are here. So, analog communication, the main differentiating factor is that the source is a continuous time waveform. And then I should put this here with digital communication. As digital conveys, the source is typically digital, meaning binary. But of course, you could have some abstraction where you're sending non-binary information that is still, somehow finite here. So digital communication systems are built around sending, binary information, strings of bits, sequences of bits. And analog communication systems are built around sending waveforms. And you can think about a record as being a source for an analog waveform. There's a modulated signal that's inscribed in the circles of the record there. And a CD, well, CD is probably dating me here, but let's say, the information as it's stored on your smartphone is in a digital format already. And so, until many years ago, most everything that we did was analog. When we're talking, we're speaking analog. We're not speaking in bits. And communication systems were built to send analog information, AM radio, FM radio. These were all designed for communicating these analog waveforms. Now, and digital now has become popular because of the prevalence of digital sources. So one thing I want to emphasize here, this is a common source of confusion, is that both analog and digital systems use, or let's say, I should say, send a continuous time waveform. So essentially here, in an analog system, you might have a source message that, it's just some function here, and then to communicate this signal, maybe we map it onto some communication waveform. And if we were doing, something like analog modulation, amplitude modulation, it might look something like this here. Oh, terrible. All right, and then digital communication signal will have a sequence here, discrete time sequence that is quantized. So let's call this say B of n. So using discrete time notation, so this might be a 1, this would be a 0 here, so this could be 0, 0, 1, 1, for example. So this corresponds to 1, 0, 0, 1, 1. And then yet, somehow or the other, this ends up being mapped to, again, a continuous waveform. I'm just making this up, but we'll see that there will be waveforms that look vaguely like this here. So let me just write this over here. This is analog. And this is digital here. And the other main difference being that because we're sending a finite number of possibilities here, so this is finite number possible, this means that there's also a finite number of possible analog waveforms we're sending. Whereas here you could end up sending really any continuous value. You can think of it's like here we have a real number, and here we have just this binary information. Okay, so that's analog versus digital. Now I'll talk about why digital communication. I mean, any questions just on the difference between analog and digital? Question? Fault tolerance. Yeah. So, what do you mean? Like, which is better, or which is? Yeah. Yeah. So digital, it has a lot of exactly has a lot of advantages. So one of those being the fault tolerance, and it comes from the finite number of possible waveforms here. And we'll see, and this is something that we're going to do in the course, that you'll see how having this finite number of waveforms gives you potentially better error probability. Any other questions about analog versus digital? All right, so let's continue on with some of the reasons that we might be interested in digital communication, if you're not already convinced here. So this is essentially just a laundry list of possible explanations, and so I'll just kind of list them in various order here. So first of all, we had the point already mentioned, fault tolerance. This, which really amounts to a couple different points. There's robustness to noise and more resilience to analog imperfections. So whenever you build a circuit, if you're using analog components like transistors and so on, I mean, if you built like an audio amplifier, you have to spend like a lot of time matching the characteristics of the transistors, getting everything balanced. And you don't need to do that in a digital circuit, because you don't care exactly the gains, because we're really just trying to convey kind of like a 1 or a 0. So there's that's one of the benefits of digital communication here. It's sort of an obvious one here, but I mean, it's suitable for digital data. I mean, for the most part, we are generating and storing, data digitally now. So if you want to communicate it using analog, perfectly possible. You would have to convert that digital into some sort of analog waveform, and then use an analog communication technique to send it. You could do that. Not very efficient, though, it turns out. Let's see, other reasons here. I mean, here's one that's, let's say, non-technical here, but I'll go ahead and make this statement here. I mean, analog communication is effectively dead. And so what this means, if you're looking for a job at some point, is that, well, there's, no jobs and few opportunities. And what I mean by this is that, first of all, I don't mean that there's no opportunity in the analog part of communication, on the RF circuits, doing mixed signal IC design, all of that, huge opportunities there on the circuit side. But what I mean is that, people are not designing any more communication signals based on analog. I mean, the ones we have, AM, about 100 years old, FM, let's say 90 years old. And so these communication systems were designed many, many years ago. People just aren't designing new ones anymore because they're just not efficient. So yet another reason why it's not so important. And this is probably one of the biggest reasons that we eliminated this class at UT about 2005, because it just was a relic of the past. You know, at some point, right, we had vacuum tubes in our program, and then we got rid of them. And that's perhaps a different example, because there at least is niche cases where vacuum tubes are still really important. But analog, as far as innovation, I don't know. I guess there's other things I have on my list here. I guess I want to see what you think about digital communication. So can I have some other potential benefits here? Digital comm. Anyone have some more suggestions?
Data compression.
Yeah, that's a good point here. I mean, compression is possible. Now, I suspect that there's some smart people somewhere that have developed some analog compression techniques, but this is probably a lot easier to do on paper than they are to actually build. So compression is possible, if not easy. And one of the things that does is that makes the system very efficient. And the reason it does that is that it comes back to this notion of information. If there's a lot of redundancy in the source, when you send it over the communication link, you're sending a lot of extra stuff. And so if you can compress that, you can send only the newest pieces. You know, so think about a file. I mean, if you have a really redundant file and you zip it, you can make it a lot smaller. And the recipient can still recover the exact file. I mean, it's kind of like, it's amazing, but it's because there's redundancy in that file. You know, in some files, if you zip them, they don't compress at all. Like I had this happen yesterday with I was trying to mail someone a big PowerPoint file. So I thought, oh, okay, I'll just zip it and that'll work. Nope, zipping it didn't compress it at all. Kind of weird. Converted it to PDF, that didn't compress it at all. Then I zipped the PDF, that didn't compress it at all. You know, so it was a file that just had a lot of good information in it, I guess. What can I say? So compression is important. What other reasons do you all think of? Yeah, so what kind of signal processing? Oh, digital signal processing. Yeah, you got it exactly right here, digital signal processing. Yeah, but basically, right, signal processing. Pretty much all signal processing now, we just think of digital automatically. But that's really what I mean here. So digital signal processing is easy. And a side benefit of this is that you get to take advantage of Moore's law. So Moore's law, the densification of chips, fitting more transistors in unit area. So what this means is that you can take a digital signal processing algorithm, and over time, it'll fit in a smaller and smaller area on a chip. And then thus the cost actually decreases, the power efficiency improves. So there's, let's say cost, power benefits. And this doesn't really happen with analog. If you start shrinking the analog transistors, they tend to behave poorly. And and then you don't also get these kind of cost savings because they still end up being pretty big. So you don't get to integrate 1 billion of them in a centimeter. You get to integrate, several of them. So I mean, digital signal processing is huge, and this is one of the reasons that the course here is really built on digital signal processing foundations, because it is so integral to communication systems. Okay, other comments here? Any other ideas? So I'm thinking of selling like advertising on my cup here. What do you think? Can I do that? Anyone willing to advertise? I'm advertising the Wireless Center right now. I don't know, this probably won't show up in the video, but anyways. You can't see this on the video. I have a cup here with the WNCG logo on it. Okay, so, I mean, other benefits here. So there's a whole host more. So easier to implement security. That's very important. Also depends on your perspective on who you want to be secured from. I won't go into that, but there's a lot of reasons that one might want to just have a private conversation that not everyone in the government or the world is listening to. There's also it's easy to multiplex users to share the channel. So with analog modulations, primarily the way we were sharing the channel, you can share it, modulating signals at different carriers, but it's rather cumbersome. If you've got hundreds of users that want to share the same 1 megahertz of bandwidth, it's a bit easier to do with digital. So we have, let's see, the robustness, uses the high-quality digital components. Sort of mentioned that somewhere here. Yeah. So that's I guess the main reasons here. So is anyone not convinced that we should use digital communication? I mean, am I missing something here? I'm not trying to oversell it, but the reality is that this is the de facto form of wireless communication now, and that's why we focus on that in this course. Not to say that we won't deal with continuous time waveforms. We will. I mean, we will use continuous time signal processing in the course, but we will not do analog signal processing. We'll essentially very quickly sample that signal and do everything in digital. And on the transmit side, we're going to do everything in digital, have a digital to analog converter, and then ship it over the channel and put it back into digital as quickly as we can. All right. Any questions on this part? So now we're going to transition to the second part here. So now, a few of you have taken my class before, and you know what's coming here. So there's a lot of theory actually on teaching. Like in every subject, it seems, there's people that do theory. And so there's people that study concepts like attention span. So how long are you all paying attention to my lecture? Especially I'm like sitting up here, speaking in a monotonous voice. It's 9 a.m. A good fraction of you will be sleeping by the end of the lecture, and it's understandable. Now, so one of the, I got this from, I forgot to put the book here, but I got this out of a book here. So this is a graph of a typical attention span of students here. So note that, there's this small peak here. I guess this is, the initial excitement of being in the class. And then, this is like kind of typical RC curve here, exponential decrease here, point below which lecture is useless, occurring at time Tmax here. Now, the question is, what is actually Tmax? And this depends on many different parameters, and I suppose it's instructor dependent, time of day dependent. If it's after lunch, it's different here. But this is usually on the order of somewhere between, what would you all guess, first of all? 40 minutes, 30 minutes? It's typically somewhere between 5 and 15 minutes. Probably closer to 5. Now, I've seen other work that does give a more complicated picture of the story here. So it doesn't necessarily decrease. I mean, there can be bumps and things, but as a point to talk about, this is kind of a typical scenario in the classroom here, and this is one of the reasons that lecturing isn't a super effective means of communication, because it's primarily me talking and you listening. As one of the reasons I really like having a lab component, because you're going to get the opportunity to experiment in the lab with many of the concepts we talk about in class, even if it's not like a dialogue in class. So one of the problems is this is basically somewhere between 5 and 15 minutes, and already it's now 30 minutes into the lecture. So that's a problem here. So many of you maybe have passed off at this point here. So what I try to do in the class, I don't always do it, but I try to do it, is stop at some point in the middle of the lecture and talk about something else, maybe completely random, just to essentially reset this clock here, right? So if we talk about something completely random, I feel like what we'll do is we'll reset that. And so then you'll get another 5 to 15 minutes of attention. And as from the perspective of an investment, I've just doubled the value you get out of the class, right? So now you get 10 minutes per lecture instead of 5. So I think it's a good thing to do. Question would be, why don't I stop like every 5 minutes and reset it? I don't know. I'm trying to stop for questions. It's a good point. I mean, some of my colleagues are experimenting with things like flipped classrooms. Like, for example, if after this year, when I have all the videos recorded, the class could become, I ask you all to watch the video, and then you come to class and just ask me questions. I mean, that could be like what the class becomes. I mean, I suppose I could do that now. I could record all the videos a week in advance and then try it out. But I don't know. I'd like to do this. I'd like to do it this way, because if I record them in advance, I'm talking to myself in an empty room, and it actually is not as good. So anyways, that's something down the future. And so what I'll try to do is stop and talk about things often news related, because a lot is happening in wireless. Companies are being bought and sold. New technologies are coming out. So I'll try to stop and talk about something that's happening or something that's going on at UT. I'll try not to give too many of my controversial opinions, because this will be on video and other people might see it in the future here. Okay, so now we're going to transition to the second part of the lecture here, which will eat up basically all the rest of the time, and I'm going to really try not to not finish this piece, because I noticed in the last 4 years I taught the class I didn't finish it. I had to go over the next lecture. But essentially what we're going to do right now is we're going to talk about the components of a digital communication system. So essentially we're going to talk about typical blocks and their functions. Now we're just providing some background here, because what we're going to do throughout the course is we're going to zoom in on these different functions and add more and more detail to them. And then by the end of the class, you'll build an incredibly complicated looking block diagram that describes just a piece of the digital communication system. So things you should be able to do, though, is you should be able to draw the block diagram, the basic block diagram that I have, explain intuitively what each piece does. And then as we go through the course, you'll expand on that. And then I'll also define more terminology as we go. So that's the plan here. So now let's start off with, let me find my picture here. Man. Picture. Okay. I had this bright idea of printing out the block diagram so I don't have to draw it again. I'm realizing now I may also have had the bright idea of leaving it in my printer. Oh, shoot. Okay. All right. All right, I got 2 of 3 figures I wanted. I guess I have to draw the first one. Okay. That's annoying. Let's see. Okay. All right, so this was components of digital communication system. Okay, so we're going to start off with this block diagram that I'll proceed to explain each piece here. So the top part starts with, so this right here is a TX. So this is how we abbreviate transmitter. So for the most part, I'll never write transmitter again. I'll just write TX, and RX will be receiver. So we start off with the source. So I'm going to draw everything here as a block here. So the source, and then let's see here. I'm trying to follow my the format that I'm using in the notes here. So you have then a source encoder. This is performing compression on the source. And then this could happen here and this could happen elsewhere, but you possibly have some sort of encryption. As I'll explain in more detail what each of these blocks is. So first I need to draw the whole diagram. So encryption, and then we have channel coding. So the channel code is going to add redundancy into the signal so that we can correct for errors. And then there's going to be this piece which is modulation. And then, let's see, what else am I missing here? Channel modulation. Yeah. And then I have this block here that I'm just calling generically channel. And so channel is not part of the transmitter, and you can think about the channel block as including a analog piece This would be like analog front end, propagation medium, and then more analog components here. So this is what is contained in this box here. And then what we do to process the signal at the receiver, so I'm going to now draw a dashed line here, and I'll talk about the receive blocks. And so then essentially each of these blocks here has its inverse. And so the inverse of the modulator is not inv modulator, it's demodulator. So put that here, demodulate. Okay. Then there's channel decode. Nice. Yeah, it actually looks better on the screen than how I'm drawing it. That's good. Really good. All right, so decryption. I'll just put decrypt here. And this will be the source decoder. And then this will go back to the sink here. So this is the a typical block diagram of the components of a digital communication system. Real system is naturally much more complicated. Some of these pieces might be missing. Some might be interchanged with others. But this is just a typical scenario here. Now, where we're going to focus in most of the class is really going to be on what happens here. So this is wireless communications lab. And so we will spend lectures talking about how we model this from a signal processing perspective. We'll build up a signal processing model for the modulator and for the demodulator, and we'll break that up into its own block diagram. And then we'll keep adding complexities. That's more or less what we're going to do in essentially lectures, let's say 5 through 20 is expanding on these pieces here. And in the lab, you're going to focus primarily on transmitting uncoded information over the communication channel. So we have some coding in the lab, but we just tend to not do it. We don't do any encryption. We don't do any compression. But the way these things are here, again, so this is source, compress as much as possible, add possibly encryption. This is where we're implementing some security, add redundancy to correct errors, and then modulate, just convert these bits into some kind of an analog waveform. So that's essentially the main things that you want to remember here. The encryption, notice that, you could think about having the encryption over here after the source. But if you do, you probably won't have much redundancy left to compress. So a lot of times you'll see maybe encryption or some security here, and there'll be no source coder because the application's already done the compression. So that's another modification you see. And then at the receiver here, a lot of times, see, I have demodulate and decode as separate blocks. A lot of times these are done jointly, all together, and the decrypt is done elsewhere, and the source decoding may not be here. So that's a typical system. So what we'll do now is we'll talk about each of these pieces. Any questions on this, or can't read something? If you can't read something I've written, please let me know. This is always happens that, 5 or 10 lectures in, someone in the back of the room says, hey, I actually haven't been able to read what you've been writing for the last 10 lectures. So if that's the case, please, tell me ahead of time. If you don't want to tell me, you can send me an email. If you don't want to send me an email, you can give the TA a message. If you don't want to give the TA a message, then you can slip an anonymous note under my door, I suppose. But better if you just can't read it, just tell me now. It's called the feedback. Now, I wanted to tell you a little bit about, what real communication system block diagram looks like. And so I printed out just a couple examples for you here. So you obviously don't need to write this down here. But this comes from the IEEE 802.11 standard, and this is actually the a description of the physical layer for what we typically call 802.11a, and we will talk about this like later in the course. But I just wanted to show you what, you know, a block diagram looks like in practice here. And so what you see here is this FEC, this is forward error correction, so that's actually the encoding block. And then all of these things here, essentially, and this sort of half of it, the way they've drawn it here, basically corresponds to the what you could think of as being modulation. And then this piece here over to here corresponds to what I'm calling a channel. And then this would be the demodulate right here. And so these are, this is like an oscillator. So there's a digital to analog converter embedded in here. This is an oscillator used for up conversion. So we'll talk about that as we go on. This is high power amplifier. That's an antenna. This is an antenna. That's a low noise amplifier. That's another oscillator here, modulator, down conversion. Automatic gain control amplifier. There's a digital to analog converter somewhere probably in the edge of this here. So I just wanted to give you a sense of what, you know, other block diagrams look like. And this is the kind of diagram, these pieces, this we'll be doing later in the class. So that's part of 11A. The other one I wanted to show you was, hold on a sec here, let me write 5. Oh yeah, I got this off of, this is actually GSM reference. This comes from a document. It's called 3GPP TS 45.001 version 11.0.0 release 11. This is the ETSI number here. You can find this online. This is actually the specification for GSM. It's actually GSM 2+, so it's essentially Edge. So this is the kind of a block diagram that they have as part of their standard here. So there's information bits here. This is the source. This is, you see this right here, code 1 and code 2? These are two different kinds of error control coding. Each of them has a different purpose. So, you know, when I'm drawing coding, it doesn't necessarily mean one kind of code. It could be several. Because different codes can correct different kinds of errors. There's reordering and partitioning, that's just kind of, and interleaving, that's just putting bits in different places. Now look what's here. Cryptological unit, that is the security piece. Here it appears after the coding. So, you know, there's no problem with that. It just happens to appear over here. And then this is still the transmitter, and this is all about how we map the bits onto, partially onto the waveform. This is really about the GSM, the time division multiple access technique. So this is part of building the physical layer bit sequence is here and adding the training data, known information. This is part of the modulation here. And then the abstract, you know, channel right here. So, you know, we'll go through this in more detail also later in the course. But again, I just wanted to show you, you know, some other examples of what, you know, this block diagram could look like in a real system. Now, I was trying to find the one for the most recent LTE standard, and I wasn't able to find it. So if anyone knows where that is, let me know. The annoying thing about the 3GPP standards is that, and I'm saying this publicly so someone will read this and make this change, it's very hard to search for information in the document. They have this nice web page that's got this like hierarchy of documents, but it's not like IEEE Explorer or Google where you can go and search and find something. I mean, it's just incredibly difficult, at least for academics who are not working, you know, in these standards all the time, to find, like, you know, I just wanted to find this diagram in LTE. You know, how do I formulate that query? I don't know. How do I get that information? You know, I don't know where it is. And you can see the intuitive, you know, labeling, TS 45.001. That's not so obvious to me what that means, but they do have a mapping of labels. And then, you know, you click in, and then there's another, you know, 100 set of documents, 45 dot something. And then there's another 100 set of, and then there's also revisions. This is release 11, version 11. So there's like 20 releases, 20 versions of this document there. Anyways, hard to find the newer ones, but I hope to find that at some point and include it as an example. Okay, so that's the block diagram. So essentially, in the half hour that we have remaining, I will talk about some of these different pieces in more detail. Just trying to provide some highlights of, mostly just of the terminology here. So the source encoder and decoder, these blocks here, their main purpose is to perform compression on the encoder side, and then it's to reverse that operation on the decoder side here. And the things to know about source encoders is that they can be lossy or lossless. So a lossy encoder means that there is some information that is irretrievably discarded. So I'll put that down here. Information discarded away. Great example of this, you go into Photoshop or whatever your favorite photo editing application is, and you save as JPEG, and then it gives you all these different options. What quality do you want to save at? Do you want quality between 1 and 10? What size? Whenever you make all those choices, it performs a compression on your image there. And then if you save it again, even using the same settings, it'll get smaller, a little bit smaller, a little bit smaller, but you keep throwing away information. And so, if you were trying to create like a poster-sized print and then you compressed it too much, when you blew it up to print, it would look all pixelated and ugly. So that's lossy compression here. Now, suppose that you were uploading or downloading an update for your operating system. Well, you don't want that to be lossily compressed because you just lose information. So that's where lossless compression comes in. So this is where information is retained, but it still gets smaller. And so the example of this is that zip encoding I mentioned earlier, Wimpel-Ziv encoding. It's a type of an arithmetic code that uses structure in the bit sequence to create a new file that's smaller. And you get exactly the same information in and out. And of course you have to have that. I mean, if your operating system, a few bits are screwed up there, your computer crashes or something possibly worse could happen. So this is the things about lossless and lossy compression. So lossy compression is really tied to the application. So if it's speech you're talking about, or audio, there's speech vocoders. A lot of them are specified in the standards that they're designed to compress voice. There's audio encoders, there's like MP4, there's lossless encoders. I mean, there's all kinds of different audio. I mean, you've got image, you've got JPEG, you've got MPEG for video, H.264 for video. So a lot of the, if you're interested in like, especially lossy encoding and decoding, that would be done in like either an audio or a video or an image processing class. So Albovic's sequence of classes, for example, will deal with lossy and the effects on the human brain. There's all kinds of interesting aspects there. Lossless encoding, for the most part, is talked about in the information theory course, and I don't know that we have other courses that talk about lossless too much, but the principle of lossless encoding is talked about there, usually. So that's the source encoding, decoding here. So interesting, but not something, and it's DSP related, but just not something we have time to do. So the encryption piece and decryption, this is essentially just about, it's a component of a security protocol. So the whole notion of security is something that is typically implemented in the different layers of a communication system. It's not just at the physical layer. It can happen at the MAC, the network, the transport, higher layers, and we don't deal with that at all in the class, and probably some of you really like security and you're mad that we don't deal with it, but that's another thing that we just don't have time to do. We have whole classes on, even just the topics of encryption. Probably the most well-known, at least for me, example of this is like public key encryption. And so in here, you have to exchange a key. And so you have a public and a private key, and you encrypt your message with a private key, and someone who has your public key can decrypt it and read it. It's sort of an interesting way of, also does a bit of authentication as well, because if you're the only person that has your private key, then they also know it's from, you're the sender here. And there's authentication is another piece of all of this that I'm not talking about here. So essentially, this is important. It's part of many communication systems, like I showed you here in the GSM, right here, this cryptological unit. But is GSM secure? Does anyone know the answer to this? Indeed, it is not, because that encryption actually has been hacked, and so we know how to decrypt it. And you can go on the web and download software to do this, and so you can actually capture GSM signals over the air and decrypt them. Now we'll get into the legality of it. I mean, if you can download, I don't know. I don't actually know that it's illegal to do that, but I'm just telling you it is available online, that you can find this out here. And that's one of the challenges with encryption and security in general, is that a lot of these things, encryption techniques, are just based on decrypting, if you don't know, like the key, for example, just being hard. But being hard is something that changes over time as you get more computationally efficient computers, or you start getting into quantum computing or something. Then things that were hard become easier. And so that's what happened with GSM, designed in the 80s, and now 20 years later, someone was able to crack that and decrypt it. So keep that in mind when you're having some nice private conversation on your phone here. So encryption, let's talk about a bit more about channel coding. This is an important area that is most related to what we do in the class and yet don't do. So the basic idea, as I mentioned here, is to add known redundancy to correct channel errors. Now this may seem strange at first, that we over here in the source encoder, we went to a lot of effort potentially to remove redundancy, and then we're now going to go through a lot of effort to add redundancy back in. The reason that we have these two steps is that in the second step here, we're adding redundancy in a careful and controlled fashion, so that we can use properties of that redundancy to correct errors. So a typical error would be, for example, I have 10 bits to send. So instead of sending those 10 bits, I'll send 20 bits. And if you design the code correctly that maps 10 bits into 20, you could correct maybe 2 errors. If you flip any of those 2 bits, we can still determine the original message of 10 bits I wanted to send. That's kind of the idea of channel coding here. So there's a lot of interesting mathematical aspects of coding. They're pretty cool. So I'll talk a little bit more about this here. Now, before I talk about some of the forward error correction techniques here, I want to mention 2 of the things that we typically do with channel coding in wireless. The first is error correction. That's the example I just gave. So we fix, let's see, what do I want to say? Fix, well, let's say repair receive signal. Now another thing that we do with channel coding, actually this is very important as well. This is used widely in networking protocols, is error detection. So this is where you determine if there was an error. And the most common example of this is called the CRC, the cyclic redundancy check. And this is important because, especially at higher layers, right? So we used this example earlier of, you're downloading an update for your operating system. Well, one of the things it does, and if you've had this experience before, it downloads the file and then it checks it to make sure it's valid. And if it's not valid, it doesn't try to install it. It says, sorry, there was an error. Do you want to download it again? So that's something that you can do with error detection. The internet uses this all the time to determine, were packets delivered correctly or not. We use this in wireless to determine if there was an error in a packet before sending it to a higher layer. So, and the difference here is that to detect an error, you tend to have to add only a little bit of information. So we could take, 10,024 bytes and add only, 4 bytes of information to detect if there's an error. Whereas if you had only 4 bytes to correct errors, you wouldn't be able to correct probably even 1 bit error there. So the error detection is, and you can also do it with very low complexity using this cyclic redundancy check code here. So this is important, and it's typically implemented as part of a higher layer. So the stuff that we do at the physical layer, all we're going to do is we're going to take our decoded bits and we're going to pass them up to the medium access control protocol, the link layer. And then the link layer might determine, hey, were those bits sent correctly? If they weren't, it'll then say, hey, transmitter, send those bits again. And so that's part of the link layer protocol. And so we don't deal with that much in class, and so I wanted to talk more about that here. So now I'll talk more about error control codes, also call it forward error correction. So one thing to note is that this notion of code rate. So code rate is essentially the number of uncoded bits divided by the number of coded bits. There's other ways to define code rate when you use coded modulation. So this is just a basic definition here. Now, as far as, I guess I'll shift over here to new page. Ooh, I have a white page here. Okay, so just a little bit of, history of error control codes. So, history of forward error correction, or FEC for short. So it just happens, and I don't know fundamentally why this is, but roughly speaking, there's been an innovation in error correction theory about every 10 years. And so every 10 years, something new comes along, and then people jump on that, start working on it. And sometimes it's successful, and sometimes it's not. And so I'll start off with the kind of earliest form here, which is what's called the block code. And this was developed originally, actually even started in the late 40s, but it was, but primarily researched in the 50s. So even though it was developed a little bit earlier here. And so the idea is so what is meant here by a block here is you take, say, a block of bits and produce a longer block. And so as an example, so a rate 1/2 block code would take, so could block code that's of length, let's see, well, the length depends on, you're talking about the length of the input or the output. Let's talk about the input here. So then 5 bits get converted to 10 coded bits. And you often use now coding people who write this in a slightly different way, but you could have a vector of your bits 1 through 5 here, and you could operate on this vector using a matrix. So for example, I could have a matrix that had 1s on the diagonal, and this operation would be in the Galois field too, in where we can do binary arithmetic. And so you could have, like, I'm not guaranteeing this code that I'm making up actually works well. I do have some examples in the book, though. and then these are zeros here. And so this is, 5, this is 10 bits here. And so you multiply this out, and then the output would give you your coded bit sequence, C1, C2 through C10. Now, one thing I've done with the structure of this code as an illustration is this right here is an identity matrix here. So what you find is that the first 5 bits here correspond to the 5 bits that you want to send. And the rest of these are different parity checks. And a code that has this kind of format is called systematic. So systematic means that the uncoded bits are present in the coded bit stream. If it's not systematic, and a lot of codes are not, if there's no error, you still have to perform the decoding. Here, if there was no error, we could just, look at the first 5 bits and be done with it here. So anyways, that's just a type of a coding here. How you would do the decoding here is you could imagine here multiplying through by a left inverse and essentially another matrix here such that you get out an identity, and that would be kind of like a decoding. So the decoding is very simple. It involves basically taking linear combinations of these different observations, and you can produce these bits here. So that's a short explanation of what is essentially covered in a whole semester-long course on coding theory. Any questions on that? Maybe it's too much. So we won't design codes in the class. We won't use them. But this is, I think, probably the easiest example to understand. All right, so in the time we have, I'll keep going here. So block codes, they are used in almost every wireless system. I mean, the CRC is an example of a block code. There's also what's called the Reed-Solomon code. And then there's various other codes that are also used, like in GSM, it's called the FIRE code. And there's also BCH. But these are the CRC, the Reed-Solomon is very common. So block codes are used in all the systems that are commercially interesting here, despite being developed more than 50 years ago. Okay, so another type of coding that is also very important in wireless is convolutional code. And this is developed in the 60s and kind of late 60s, early 70s here. And essentially the way to think about this is the notion of convolution comes from, indeed, linear systems theory here. So you actually you convolve data with multiple impulse responses. And there's various, ways to implement this and simplify it and make it more complicated. So I'll give you just an example here. So suppose I had a bit sequence B of n. I take this bit sequence, and I'm going to filter it by an FIR filter G1 of k here. I'm going to do all the filtering in binary field. And I'm going to filter it by another filter G2 of k here. So these are, let's say, FIR length nu plus 1. Nu is usually the constraint length. It's the amount of memory. So I just do that convolution, and then at the output here, I just interleave the outputs. And so you can see that, this bit stream creates 2 filtered versions of that bit stream that we then end up interleaving together. And we have a little bit of a tail, too. So there's that tail is there, and there's various ways to deal with that tail. And usually you initialize these with zeros. So that's an example of a rate 1/2 convolutional code. And so there's many variations of this. Rate 1/2 convolutional code is used in GSM. It's used in 802.11. It's used in IS-95, wideband CDMA. So convolutional codes are used all over the place as well. So an example, this is an example I have from my notes here. I forget where I got this example here, but so for example, my coded bit stream here, I could create every even output by taking the binary sum of the current and previous bit. And I could create every odd output by taking the binary sum of the current and the second previous bit here. So this is, as you can see here, is just a simple FIR filtering operation, and I'm just using the 2n here because that's the interleaving operation here. Now, one thing to note with convolutional codes is that the decoding is important, and it's also complex. Complex meaning complicated, not in the complex field necessarily here. So there's a whole bunch of different types of decoding algorithms. The most common one is called the Viterbi decoder. And, man, don't know how to explain the Viterbi decoder in like a fraction of a lecture here. Essentially, when you take this bit sequence here and convolve it together, you get a very long bit sequence out. So the Viterbi decoder, what it tries to do is find the best sequence that's closest to what you observe. And because of the memory in the system, it can do this in a very nice recursive manner. And so it's sort of a cute algorithm. Fortunately, won't have time to go through it, but it's a cute algorithm in the sense that it would take a whole lecture to explain it, and it would take like a week or two to probably implement it. But it is important. So that's like a Viterbi decoder, and then there's other better decoders as well. And some of these are used in other kinds of codes, called iterative decoders. So that's convolutional codes. Now, see how much time I have here. All right, so rapidly running out of time. Trellis code. This is like developed in the 80s. Now, these have not seen wide use in wireless. The only place I can think of in wireless is the U.S. Terrestrial digital video broadcasting system uses a trellis code. But for the most part, they only had impact in wireline modems. But a trellis code, actually, it's a really, really cool thing. So it's an example of what's called coded modulation. So in a sense, this, so we'll talk about modulation in, oh man, all right, rapidly running out of time here. We'll talk about modulation in a minute here, but basically these bits are mapped into complex numbers. So the trellis code does that operation at once. Instead of filtering the bits and then mapping, it does the mapping at the same time as the encoding. So it's combined coding and modulation together. It's kind of cool, and it uses a similar type of Viterbi decoder, but yeah, it hasn't seen like wide use in wireless. And one of the reasons is that you're typically then tied to a modulation. And what we'll see later in the class is that when you use a convolutional code, you can change the modulation. And we like to change the modulation based on what's happening in the propagation environment. All right, so that's trellis coding. I put Viterbi decoder here. All right, time. Okay, so turbo codes. So turbo codes were developed in 90s, in particular, 93. And it's actually just sort of a miraculously cool idea that has a couple different cute features, but it's like to me, it's a tricky extension of convolutional coding. So it involves filtering with an IIR instead of an FIR filter, plus interleaving between the branches. So meaning that if you have B of n coming in, here it goes into an IIR filter, and here there's an interleaving operation, and then it gets filtered by another filter here. Same with this multiplexing operation here. And in addition to that, it uses a very special kind of an iterative, what's called an iterative decoder. And so it's a special decoder. It ends up being about 4 times more complicated than the Viterbi algorithm, but it allows you to essentially use part of the data to make a guess. And you take that guess, and you use the other part of the data to refine your guess. And you take that refined guess, and then use the original piece of data to refine your guess further. It turns out that by designing this interleaver and these polynomials correctly, you can actually improve each time up till some point and get very, very low error rates. And so these turbo codes, in theory, get very, very close to the fundamental best that you could do. And so they've been used in wideband CDMA, not as widely used in other wireless systems. One of the reasons is that you typically need long block lengths. So here you might need thousands of bits. This interleaver has to be thousands of bits long, and often that's just too big. So LDPC codes, low density parity check codes, were developed in 2000s, though their origin actually goes back into the 60s. So this is essentially block code plus smart decoder. And I'm trying to think here if they've been used in any. I've seen them proposed in various wireless systems. They are used in some of the millimeter wave specifications. I forget if it's, I want to say WiGig, which is 802.11 AD. I think they're used there. So this has been relatively recent that they've been used. Now, the question of being, what is the next hot coding topic? Probably polar codes, but maybe it's too early to tell. So I'll just put polar codes here with a question mark. These have gotten popular in the last 5 years or so, but they're not yet used in any wireless system that I know about. Okay, so that's essentially coding here. I seem to have covered exactly what I always cover, which doesn't include modulation for some reason. I don't know how this happened here. I think I forgot about the modulation piece. Anyways, we're going to talk a lot about modulation, so I don't feel like it's a massive loss here at this point. We'll talk about it more later. So let me review some of the key concepts here. So essentially, coming back to what we did in the first part of the lecture, we need to be able to explain why digital communication is important. Why are you studying digital communication in this class? Why is it interesting for the future? What are its benefits over analog? And then there's a lot of different aspects of it: circuits, signal processing. So you should be able to articulate those examples. And then in the second part, what we talked about were the components of the digital communication system. And so you should be able to essentially draw out that block diagram that I have right here. So you should be able to draw out this diagram and then explain at a high level what each of these pieces do. And then later in the course, you should be able to provide a very specific mathematical description of the modulators and the demodulators. And that we're going to do. You can see that already in chapters 3 and then 4. Oh. Okay, that's it for the lecture here. One thing to note is that we don't have a formal lab this week. We will have a tutorial session on LabVIEW, which is held during the Thursday lab. If you cannot make the Thursday lab, the slides will be posted online, but please try to make that, because we're just going to have the tutorial in a separate room, a bigger room than the lab. And then we'll start with the actual labs, Lab 1.1 next week. The main thing you want to really do now is just get familiar with LabVIEW. If you're not familiar with it, the more time you spend in just learning the basics, it'll pay off later. Yes? It's just LabVIEW basics because we actually don't use the modulation toolkit because much of what you're going to end up doing is creating functions that are already in the modulation toolkit. Yeah, that's kind of, I mean, and maybe it seems redundant, but the principle, you know, so you could just go in there and drag in the QAM modulator and like be done with the first 3 labs. But there's a lot to understanding what actually goes into the modulator, and it's even more important on the DMod side. So yeah, so if you're familiar with LabVIEW, you know, you don't necessarily have to feel compelled to go, and I know many of you have programmed in the past. So there won't be, I forget if there's any USRP specific information. Any other questions? Right, so I'll be in my office for the next hour and a half or so. If you want to stop by, thank you.